So here we have a What the Physics video for projectile motion type 2 problems. That is angled launch with a zero displacement on the y-axis. We have a ball is thrown at 4.47 meters per second with an angle of 66 degrees above the horizontal. A, what was the ball's hang time? B, how high did the ball go? And C, what was the range? So after we draw it out, the first thing we are going to do is, of course, put it up on here. Let's see. We got a lovely angle right here. That's theta, even though I know it's 66 degrees. Right now I'm just labeling things. I'm going to call this V naught. This is V naught is kind of a British thing, but anyhow, I don't want to call it V initial because I've been using V initial for the y-axis. So, and of course we have acceleration is downwards. That's going to be acceleration due to gravity, but that's an okay drawing to start with. Let's go ahead and make some lists, and we've got stuff going on. Let's change up some colors here. We've got stuff going on the y-axis. We have initial velocity, final velocity, acceleration, displacement, and time. And then on the x-axis, we have there is no acceleration on the x-axis, so I'm just going to draw one velocity, and that's v sub x. As I just mentioned, there's no acceleration, so I'm going to say d sub x, just skipping over the acceleration, and time. And I do know that these times are the same, but that's really it. Now you say, okay, well, where should I put this 4.47 meters per second? Because it seems like that's one of the velocities. Unfortunately, it is not. The 4.47 meters per second is a velocity that is going off like this at 66 degrees. What I need to do is break that down into a lovely little y piece and a lovely little x piece. Now, to get the x, I know I'm going to be using the cosine, so r times cos theta, and then we have r times sine theta. If I actually plug in my values, this would be 4.47 meters per second times sine of 66 degrees, which is not something I can really do in my head. So tap on the calculator, and I get Vy initial is equal to 4.08, and then, ran out of room, meters per second. For the x, I'm going to have 4.47 meters per second times the cosine, 66 degrees, and that means v sub x is going to be 1.82 meters per second. So I'm just going to fill that in right here. 1.82 meters per second. And then my initial, as we said, because I have two velocities on the y, 4.08 meters per second. Lovely, lovely, lovely. Now, what else do I have? I mentioned I have acceleration due to gravity is little g, or negative 9.8 meters per second squared. Cool. And I am trying to figure out what the hang time is. So I'm looking for that, or you could say I'm looking for it on the x-axis. But I really don't have enough information for the x-axis. You say, oh, but sir, you don't have enough information on the y-axis to do it either. Oh, but wait, I definitely do. In fact, I have three different ways I could do it. Let's see. So, like I said, there's three different ways I could do this. I did not mean to do that, sorry. So one way that I could do it is I could say, and going along with my information already, I could say that this right here is my initial velocity. starting right here, and then just focusing on the y-axis, it goes up to here. And at that point, my velocity is going to be 0. So that would be like my final velocity. I could do that, or I could say, hey, you know what? Let me start from here and then go down to here, where this would be my initial velocity. Down here would be my final velocity. And my final velocity in that case would just be the negative version of this initial velocity. It would be negative 4.08. It works either way, but I don't think we'll use that, especially since I just already filled this in, and I don't want to confuse too many people. Now, if you do it either one of those ways, notice it only talks about the upward or the downwards. It does not talk about both. So if I use one of those methods, I'd have to double the time, which is perfectly fine for me to do. In fact, let's go ahead and do it one of those ways. Final velocity being 0, and I don't care about the displacement. So that means I'm going to use VVAT equation. So VF equals VI plus AT, and I know that VF is equal to 0. I bring the VI to the other side, so that's negative VI equals AT. I divide both sides by A, and I can just plug in, and I've got negative 4.08 meters per second divided by negative 9.8 meters per second squared. And notice all sorts of things are canceling out, and including the negative signs. Look at that. Okay, and in that case, I'm going to have the time on just the one trip is equal to, or the one direction of the one trip, of 0.416 seconds. Okay, so I have my time here on this method is 0.416 seconds. It would have been the exact same if I used this as my initial velocity. This is my final velocity. Anyhow, that is not the actual question, though. The question was, how long is the ball in the air? What is the ball's hang time? So I'd have to actually multiply by 2, and then I'm going to get the full hang time. So 2 times this, and I'm going to get 0.8, and we can round off, I guess, if we want, but we'll say we'll keep this extra digits for a moment. Okay, so that would work. We could have also done it a different way, and this is kind of a cool way to do it, and I'll make a quick list of the other way too. But we'd be going up and down. And with that method, which I'll do in red, I can still use 4.08 meters per second. And in this case, my final velocity, I can either ignore or I can recognize that the impact velocity is going to be the negative version of my launch velocity. Acceleration is still little g. Displacement is 0 because I go all the way up and then all the way down again. So overall, it's 0. And then I'm looking for my time. And the nice thing about this is I don't have to double my time in the very end. In this, I would use probably dy equals VIT plus 1/2 gt squared. And you might say, oh no, how can I do this, Fair? Because usually I would just get rid of the velocity right here. And if you notice, right now I have a t squared right here. I have this t here, and there's no t at all right there. By getting rid of this velocity initial, that would get rid of this time right here, and that would make things a lot easier to solve for t. We're not able to do that. Anytime we have a non-horizontal launch, we can't just get rid of the initial velocity, as it is clearly not 0. But what we can do is we can say, oh, the displacement is 0. If that's the case, subtract the v initial times t to the other side, 1/2 gt squared, and then some of the times cancel out, and I'd solve for time, and it would be, if you just plug in, it would be the 0.833 seconds, as from before. Fantastic. Fantastic. Now, how are we going to move on to part B? It says, how high did the ball go? Let us focus on the y-axis again, and I can actually use the same information as before, that I'd done over here in green. So let me bring that over here. I have, focusing on the y, I have the initial velocity, final velocity, acceleration, displacement, and time. And we have 4.08 meters per second, and I have 0, and I have little g. And this time I'm trying to figure out what my displacement is. And even though I know what the time is, I'm not going to pay any attention to it. Now you say, why? Well, I'm trying to figure out what my maximum height is right here. This is my displacement on the y-axis. That's the peak, right? And I know at the peak, my final velocity is 0. So that's a wonderful thing to keep in mind. So if I don't care about time, I'm going to use the VF squared equation. VF squared equals VI squared plus 2AD. And if you notice, this is 0. So I bring stuff around a little bit. Negative VI squared equals 2AD. Divide both sides by 2A. And I'm running out of space here, but then we can just plug into our calculator, and we get the initial velocity. That's the initial velocity on the y-axis, of course. That is going to be squared, so 4.08, and that's a negative. Let's see, meters per second. That whole thing is squared, divided by 2 times negative 9.8 meters per second squared. And the negatives will cancel, and so on and so on. We get our displacement is equal to 0.85 meters. And the nice thing about this is we can actually do a lot of these calculations in our head. If we see 4.08 here, that's effectively 4. If I square 4, 4 squared is going to be 16, yeah? 2 times 9.8, 9.8 is effectively 10, so that's going to be 2 times that. That's 16 divided by 20, which is 4/5, or 0.8. So that's a very good sign that everything is working out correctly. Also, the units will end up canceling. There's a meters squared there, and then the seconds squared cancel out. So that is all a very good sign. Then finally, part C, what was the range? Now, I'd originally written in blue up here, but, oh shoot, there's not really enough space. Well, let me do it all again. So my displacement on the x can be figured out this way. I'm rewriting the velocity on the x. That was 1.82 meters per second. My displacement on the x is what I'm going to be looking for in part C. It says, what is my range? And then my time, well, that's the time I'd gotten from before. That's this guy. Now, notice I better use the full time. I'm not going to use just the time to get up to the tippy top. I have to use the entire time. So I've got 0.833 seconds. You say, oh, which one of the big 5 equations should I use here? Man, I don't even need to use one of the big 5 equations. I've got displacement on the x equals velocity on the x times time. That was one of our equations given to us, right? It's already rearranged. We don't even need to move things around. I'm just going to say 1.82 meters per second times 0.833 seconds. And as we can see, when we plug it all in, it's a relatively small number, 1.52 meters. And I can quickly estimate that that is reasonable, because 1.82 is effectively 2, and then 0.833 is effectively 1. So it's going to be a little less than 2, as I can definitely see there. And of course, the units work out, and we are very, very excited about being able to do this. So a big thing that I want to make sure that we understand here is for an angled launch, which sometimes we call a type 2 problem, first of all, we have to break it down into the x and y pieces. And you say, why do you know it's an angled launch? Well, it said 4.47 meters per second at this angle, right? It did not say it was horizontally launched or kicked or anything. It said this. Once we get that, we say, okay, break it down using our trig functions, very, very simple. And then because the initial velocity was not zero, when we are going to be plugging in and solving for the time, we cannot simplify it by making the time equal to zero, like we had mentioned. I'm sorry, by making the initial velocity equal to zero. But there was another shortcut here because the displacement was zero. So that was very, very handy to do. Okay. Otherwise, there's wonderful things we can get from this. We can get the maximum height by saying, oh, final velocity is zero. And we can get the overall range by calculating the entire time that it's in the air and then multiplying by the velocity on the x-axis. Wonderful physics.